Hello. I was just thinking that you probably know this fact that I can write any fraction as a terminating or recurring decimal. And you might know that if I have any prime number that's not 2 or 5, then that will be a factor of the number 9999999 for the right number of nines. And you might also have come across a famous theorem in number theory called Fermat's little theorem. And it turns out that those statements I've just made, they're not just closely connected, they're nearly the same statement. And that's what I wanted to explore now.
Okay, so let's start by looking at something like 1 over 7, 0.142857, 142857, and so on. So if you like, 0.142857 recurring. So what can I do with that recurring decimal? Well, I can multiply it up by 1,000,000 by 10 to the power of 6. I'll move my decimal place 6 places to the right, and I'm left with an integer, 142857, 0.142857, and onwards. And of course, the beauty of this is that I can take these away from each other, so I'm left with 10 to the power of 6 take away 1 times a seventh is equal to 142,857. Now, that thing on the left-hand side, 10 to the power of 6 minus 1, that's just 9999999, 6 nines. Okay, and we're multiplying that by a seventh, and we're getting a whole number. So 7 has to be a factor of 999999. In this case, the right number of nines to choose was 6. And we can do this game with any prime we like, right? 1 over 13, 1 over 11. And we'll always see that 99999, where you have the number of nines being the length of that repeating unit, has a factor of p. But why are either of these the case? Right? Why is this true? So if you know anything about modular arithmetic, that's a really good language for phrasing this phenomenon, and you can do it very cleanly. So what we're asking is that 1,000,000 has remainder 1 when divided by 7. So it's 1 more than a multiple of 7. So we can say that 10 to the power of 6, 1,000,000, is equal to 1 mod 7. So that just means 1 more than a multiple of 7. And in fact, Fermat's little theorem, which I alluded to at the beginning, exactly states that if I have a prime p and a number a, which is not a multiple of p, then a to the power of p minus 1 is 1 more than a multiple of p. So it's 1 mod p. Again, I want to explain that in a little bit more detail. So what we're going to see now is that there is some number of nines for which 99999 has a factor of 7 or a factor of any other prime. And I want to start just by looking at the powers of 10 mod 7, what their remainder is after division by 7. So 10, that's equal to 3 mod 7. It's 3 more than a multiple of 7. 100 is 2 more than a multiple of 7. So 14 times 7 is 98. 1,000, well, that's 6 more than a multiple of 7. 142 times 7. 10,000, well, that's 4 more than 9,996, which is 1,428 times 7. Notice those numbers, 124, 1248, those might look familiar, and you can think about why if you would like to. So you see that those remainders we're hitting, 3, 2, 6, 4. So we're just going to keep hitting numbers there between 1 and 6. Notice we can't hit 0, because that would mean that we'd made 7 a factor, and just taking higher and higher powers of 10, you're not going to actually make 7 a factor. So let's just look at the first 6 powers of 10. So 10 to the 1, 10 to the 2, up to 10 to the 6. So either one of those has remainder 1, in which case we're done. That's our number of nines, so it's such that we've got a factor of 7 there. But if we've gone through the first 6, we've not hit a 1, then we must have had a repeat. So we must have an a and a b, such that the remainder of 10 to the a is equal to the remainder of 10 to the b after division by 7. And in fact, we can divide in this system of arithmetic. So we could say, so in fact, that means that 10 to the a minus b was equal to 1 mod 7 was 1 more than a multiple of 7. So in fact, we are done. I really just want to leave you by sort of inviting you to think a bit about this, because it's sort of neat. Right? It turns out in any base, so in binary or ternary or whatever, any fraction has a terminating or recurring expansion. And this is totally intimately linked to this famous theorem of Fermat. So thank you very, very much for listening, and I look forward to seeing you next time. I believe I left a subscribe button.